Hello everybody, my name is Iman at SAD. Welcome back. Today we're going to go ahead and finish the latter half of chapter 2, and here we're going to talk about resonance. Now, let's recall from chapter 1 when we talked about valence bond theory. We said that valence bond theory describes bonding that we now know we draw using bond line structure. Now, in regards to valence bond theory, in that first chapter, we said that there were limitations of valence bond theory that had to do with atomic orbitals, but we sort of fixed that limitation, or we sort of talked about a solution to that limitation, and that was hybridization, hybridized atomic orbitals. Now, in the previous video, we talked about how we now are going to convey molecules and compounds using bond line structure, not Lewis structure or any of the other methods, but through bond line. And now, in order to talk about resonance, well, the limitation of bond line is that some electrons are delocalized. And so that means that they actually kind of move around. They don't stay in one localized place. And so that's going to be a limitation to bond line, because how are we going to draw those delocalized electrons? Well, we're going to talk about resonance, and that's what's going to fix that for us. So resonance structures is how we are going to fix that problem with bond line. And that's going to be the topic for today. Sometimes drawing one bond line structure for a molecule isn't going to cut it. It's not going to be enough to convey what that molecule actually looks like. Why not? Because of delocalized electrons that are moving around within the molecule and not staying in one localized place. Now, you might ask, what kind of molecules have delocalized electrons? Well, that is a great question. Molecules with double bonds and lone pairs and areas near those with varying electron density is what's going to result in these resonance structures, in these delocalized electrons that we're going to draw and convey through resonance structure. We will actually cover the 5 patterns that signal resonance in a molecule and learn how to draw the resonance structures. But in other words, resonance theory is going to be used here to represent all the different ways that the same molecule can distribute its electrons. I mean, look at this example that we have right here. This drawing is one entity, one molecule. This is all the same molecule, but they're resonance hybrids of each other. The real molecule looks like a combination of all these resonance structures. The difference between each one of these structures is only the movement of electrons, which doesn't change it into a different molecule. All right, the movement of electron doesn't mean that these are different molecules. No, they are the same molecule. Simply the electrons are moving around within the structure. Now, we're going to talk about all the rules for drawing resonance structures here. All right, we're going to cover a few basic ones before we jump into the 5 patterns that we need to know in order to be able to draw the resonance structures for a molecule. Now, the first rule for drawing resonance structures is that your arrows, they're going to travel from regions of high electron density to low electron density, all right? So, first of all, the first thing that you need to know is kind of the hierarchy for high electron density to low electron density. I'm gonna write it here in the corner. All right, you might have a negative charge, for example, or a lone pair, right? Okay, that's going to be your highest electron density. Then coming up next is your double bond, and then a positive charge. So this is going from high electron density to low electron density. And so whenever you're looking at a molecule and you're trying to draw the resonance structure for it, all right, remember that you'll be drawing those arrows from high electron density to low electron density. Look at this molecule, for example. All right, if you're trying to draw the resonance structure for this molecule, all right, your arrow is going to point from high electron density, right? A double bond is higher in electron density than a positive charge. So your arrow will go from high electron density over here to low electron density. Now, of course, this is going to make more sense on how to do that when we cover the patterns, but just keep that in mind as we go. All right. Another thing that you need to keep in mind when you're drawing resonance structures is that arrows are used to convey the movement of delocalized electrons, But more importantly, the net charge of structures are going to always stay the same. All right, we're not going to try to create new net charges here. We want to make sure that we just preserve the net charge of the structure. All right, in addition, you want to avoid breaking a single bond whenever you're drawing resonance structures. You do not want to break a molecule in half or break that single bond. Like, look at this example right here. If we want to move electrons here to the positive charge, what actually ends up happening is we'll form a double bond there, but then we've broken this molecule. We never want to do that. That is so wrong. And in addition, you want to keep in mind that you're never going to exceed an octet for any of these second row elements, and that's pretty much what we're going to be dealing with. Now, keeping that in mind, and it will make more sense as we get into some problems, we're going to jump into the 5 big patterns of resonance structures, okay? So when we're able to recognize these patterns, drawing the resonance structures for molecules is going to be a lot easier this way. Actually, just recognizing that a molecule has delocalized electrons and therefore have resonance structures will be a lot easier when we know these 5 patterns. And we're going to start off with this first pattern called allylic lone pair. All right, just a quick definition here. Whenever you have a double bond, all right, whenever you have 2 atoms participating in a double bond, here are their carbons. Let's make them red. Here's a carbon and here's a carbon. They're participating in double bonds. These carbons participating in double bonds are called Allylic positions. All right, the carbons that are participating, the atoms that are participating in the double bond are called Allylic positions. That makes all the other atoms attached to those. All right, for example, this carbon that's attached to it, and this carbon that's attached to it, these are going to be called allylic positions, all right? So they're like one atom away from the atom that's participating in the double bond. All right, so here's the carbon that's participating in the double bond. One atom away from that is called an allylic position. All right, so this first pattern is called allylic lone pair. That means if you see a double bond, all right, and there's a lone pair near it, which is going to be kind of conveyed through that negative charge, then what you should be thinking is, oh, all right, this is going to be the allylic lone pair pattern. All right, I can go ahead and proceed that way. All right, so be on the lookout for a double bond or any pi bond and a lone pair near each other. That is the recipe for the allylic lone pair pattern. So look at here. We have a lone pair right next to, in the allylic position, right next to the double bond. All right, and so how this pattern is going to work, when you see a lone pair next to a double bond, all right, you know this molecule is going to have a resonance structure. All right, so how are you going to draw that out? How are you going to draw its resonance structure out? Well, you're going to start your arrow from high electron density. All right, you're going to start your arrow from high electron density, which is this negative charge. You're going to dump those negative charge right there. So that means you're going to form a double bond right here. All right, but you don't want to exceed the octet rule. If you form a double bond right here, all right, this atom is going to exceed its octet rule. So if you're going to make that bond, you have to break this bond, this double bond. And so what happens then is you're going to form a double bond right here. All right, and since you broke the other double bond, you're going to dump its electrons here at this position. All right, so we've pretty much moved the double bond and the lone pair. All right, so one more time. Okay, we see a lone pair. We see a lone pair right next to a double bond in the allylic position. All right, this is giving me a hard time. Okay, right next to the double bond, we're going to move the lone pair to form a double bond right here. And then as a consequence, we're going to break the double bond and have the double bond dump its electrons at this position right here. And so as a consequence, we form a double bond right here now. And then there's the lone pair right here. Look at how we preserved the net charge of this molecule. All right, that's a good way of double checking your work. All right, so the first pattern is called allylic lone pair. All right, you'll have a lone pair in the allylic position right there, right? See, you have a double bond right here. All right, one atom away from this carbon, you have that lone pair. All right, so you're going to be on the lookout for a double bond and a lone pair for this pattern, and you're going to use 2 arrows, all right? First arrow from the lone pair to form a double bond, and then you're going to break the other double bond that was there. Let's do a quick example right here, all right? We have a nitrogen right here with a lone pair in the allylic position from the double bond. Here's a double bond. All right. So now we know that this is going to be our allylic lone pair pattern. And how are we going to draw the resonance structure for this? Well, we're going to have to start off at the lone pair, right? At the lone pair, and we're going to dump the lone pair here to form a double bond. But if we're going to form a double bond here, we have to make sure to break this other double bond and have it dump its lone pairs at the oxygen. All right, and so now we have our double bond right here between the nitrogen and the carbon. All right, and now the oxygen has an extra lone pair. That means the oxygen has a negative charge now because it has those extra electrons. All right, and that nitrogen lost its electrons, so now it's going to have a positive charge. Look at this. We formed some charges here, a negative charge and a positive charge. But the net charge of a whole, that negative and positive, they cancel each other out. The net charge of the whole molecule is still 0, just like what we started off with. All right, so that's our first resonance pattern. All right, now our second resonance pattern is called allylic carbocation. Here, what you're going to be on the lookout for is a double bond and a carbon cation. All right, so look at here. We have this double bond. And then in the allylic position, we have a positive charge. Okay, so this pattern is called allylic carbocation. Whenever you see this, you know that this molecule is going to have a resonance structure. And all you have to do here is draw 1 arrow from the double bond to the positive charge. All we're doing is moving the double bond over, kind of like opening a door. All right, we're going to move that double bond over to the other side. And over here now we're going to form that double bond, and that positive charge is going to come here because now we've lost electron density in this area. So we put that positive charge here. All right, again, preserving the net charge of the molecule. All right, so that's our second pattern. Let's do another example. Look at this molecule. We have a double bond and an allylic, and in the allylic position we have a positive charge, a carbon cation. What are we going to do? We're going to draw the arrow from the double bond over to the other side. And we're going to form the double bond here on the other side. As a consequence, we have a positive charge now here because we lost electron density. All right, so that's how we do this second pattern. So we've done allylic lone pair. That was our first one. And now we've done allylic carbocation. That's our second resonance pattern. Our third resonance pattern is a lone pair adjacent to a carbocation. So look at here, this nitrogen has a lone pair, and it's right next to this positive charge, this carbocation. Okay, if you see a lone pair next to a carbocation right next to a carbocation, what we're going to do is we're going to draw, all right, this means this is going to have a resonance structure. We're going to draw our arrow from the lone pair over by the positive charge to form a double bond over here. All right, because we've moved this electron, all right, now we've moved the positive charge to the nitrogen. They've switched positions. Okay, so this is the third resonance structure pattern, a lone pair right next to a carbocation. Beautiful. Now, our fourth resonance structure pattern is you have some sort of pi bond between 2 atoms of differing electronegativity. So here we have a carbon, and here we have an oxygen. All right, they have different electronegativities. You can double check by just looking at your electronegativity value table. All right, they have differing electronegativity, and look at that. They have a pi bond in between them. They have a double bond. All right, so we have a pi bond between two atoms of differing electronegativity, this molecule is going to have a resonance structure. How are we going to draw this resonance structure? Well, we're going to break this double bond and have it dump its electrons at the more electronegative atom. So oxygen's more electronegative. When we break the double bond, we're going to give the electrons of the double bond to oxygen. All right, so now oxygen has those extra electrons. All right, so we've lost electron density at the carbon. We give it a positive charge now, right? And now this electron has an extra lone pair. It has that negative charge. All right, we still preserve the formal charge here. This had no net charge. All right, this negative and positive charge, they cancel each other out. So the net charge of the molecule as a whole is still 0. All right, so that's another way. You always have to double check that the net charge of your resonance structures are preserved, and we've done that here. All right, now the last resonance structure pattern is having a conjugated pi bonds encoded in a ring. All right, so you're going to be looking out for a ring structure that has pretty much conjugated pi bonds after pi bonds after pi bonds. All right, you can move these pi bonds around. All right, they can rotate around like a ring constantly. All right, and that's you drawing the resonance structure of the same molecule. All right, essentially, since in a conjugated ring, all those pi bonds can constantly move around. In a ring, we usually just draw a conjugated ring like this, right? Here's your ring, and then we draw a circle in the middle of it to convey that the electrons within this ring are constantly moving around. They're delocalized. All right, so here are our 5 patterns. We have allylic lone pair. All right, you need 2 arrows to draw the resonance structures for molecules with this pattern. Your second resonance pattern is allylic carbocation. You draw 1 curved arrow here. All right, your third resonance pattern is a lone pair that's going to be adjacent to a carbocation. All right, you're just going to move those lone pairs over. All right, so you just need 1 curved arrow. All right, your fourth resonance pattern is when you have a pi bond, some double or triple bond between 2 atoms of differing electronegativity. And your last resonance pattern is when you have a conjugated pi bonds enclosed in a ring, and you just draw 3 curved arrows around that ring to signal that the pi bonds are moving around the ring. All right, now let's get into some problems so we can really solidify this information, because it is a lot of information. All right, so we're going to go ahead and we're going to do a couple of practice problems here. All right, starting off with A. All right, we're going to go ahead and draw this out like so. All right, what do we see over here? What is one resonance pattern that we can pick up really quickly? Well, look at this. Look at this. We have a carbon and an oxygen. All right, 2 atoms of differing electronegativity with a pi bond in between them. All right, we know what we need to do now. All right, we know what we need to do. So for this, we're going to, break this double bond, and we're going to dump the electrons of the double bond at the atom that's more electronegative. All right, so we're going to break that double bond, and we're going to give those electrons to the oxygen. All right, now we're going to enclose all the resonance structures for this in brackets. That's how we always are going to convey resonance structures, right? So we're just saying, oh, look, when we enclose them in brackets, these are all the same molecule. They're simply resonance structures of each other. All right, so we're breaking the double bond. We're dumping the electrons at the oxygen. So now what we have is a structure that looks like this. This is our first resonance structure for this molecule. So that oxygen is going to have a negative charge. This carbon lost electron density, so it's going to have a positive charge. All right, cool. Now, do we see any other resonance patterns here that we can continue to draw resonance structures for? Well, look at this. double bond, and in the allylic position, we have a carbocation. Beautiful. That's another one of our patterns. All right. And when we draw this, all right, an allylic carbocation, all right, all we have to do is draw one arrow where we dump this double bond over here. All right, like a door opening. Okay. And so we're going to draw out this resonance structure now. All right, we formed a double bond there. Here's our oxygen with a negative charge. All right, since we formed a double bond here, all right, our positive charge moves over there because we now have a carbon with a loss of electron density, and it's a carbocation now. All right, so are there any new patterns here that we might recognize that we might need to move around? Anything that is unique that will result in a new resonance structure? Not at all at this point. All right, yeah, we have a negative charge right next to a double bond. All right, we have a lone pair next to a double bond, and you might say, oh, that's our allylic lone pair. Absolutely, but if you go ahead and move it here, all right, and then break the double bond, all right, and move that over there, you're not going to form any new resonance structures. All right, you're just going to go back to your old resonance structure, which is what you started off with. So that movement causes no new resonance structures, and so these are the 3 resonance structures of your first molecule A. All right, and sometimes you can go ahead and try new patterns and see if you're actually getting any unique resonance structures. All right, so that's how we're going to do A. All right, let's go ahead and do B now. All right. Here is B. All right. Do we recognize any resonance patterns here? Look at that. Double bond, and in the allylic position is a carbocation. Beautiful. That is one of our resonance patterns. Now, how do we deal with this resonance pattern? All right, we start at the double bond, and we're going to move it right over here. All right, and so what we get as a consequence of that is a structure that's going to look like this. All right, that positive charge has moved over here. All right, do we recognize any other resonance patterns here? Well, look at that. This positive charge is now next to this other double bond. All right, cool. Let's see if we can. Let's see what structure we get if we move this double bond here over there. All right, what we get now is a structure that looks like this. All right, cool. Are there any other patterns now that we recognize that we need to draw any new resonance structures? Well, we have a positive charge here right next to this double bond. But hey, if we move this over, this double bond over right here, all right, what we're going to end up with is a structure that looks like this one. Look at that. All right, we end up with a structure that looks just like the second one that we've drawn. So we're not going to get any new resonance structures by moving this. And so that means we have drawn all the resonance structures for this molecule. All right, so that's how you double check. Fantastic. Now let's go ahead and do C over here. All right, this will be the last one we do, and I'll leave D for you to try, and I'll post the solutions for it. All right, so let's go ahead and draw out C. C looks like, oops, actually, what does C look like? Alrighty, here is C. All right, let's take a close look at it. Do we see any patterns that we know of? Look at that double bond, and at the allylic position, there's a negative charge. This is allylic lone pair, and we know how to do this, right? We start at the negative charge. This lone pair is going to dump its electrons right here to form a double bond. All right, but now we have to break this double bond because we don't want this carbon to break the octet rule. All right, so we break this double bond and have it dump its electrons over here. So what we get as a consequence now is a double bond that forms here, and then our lone pair has moved over here. Now, is there any other pattern that is going to give us a unique resonance structure? Well, we have a negative charge. We have a lone pair in the allylic position to this double bond now. But if we move this around, we're just going to go back to what we started off with. So we're not getting any new resonance structures now. that means that these are the two resonance structures for the molecule. And that is pretty much how you do that. All right, I'm going to let you try out D, see if you know how to figure it out, and I'll have the answers posted in the document. Now, lastly, now we know how to recognize resonance patterns. That's fantastic. And we now know how to draw arrows appropriately to get all the resonance structures. Now, the actual structure of the molecule, the actual structure of the molecule look? It's a hybrid, a combination of all its resonance structures. So look here, we drew all the resonance structures for the molecule. The real molecule looks like a combination of all of those. However, all resonance forms do not necessarily contribute equally to the hybrid. Yes, the real structure will look like a mix of the resonance structures, like a child looks like both mom and dad, but it will sometimes resemble one structure more than the other. Kind of like how sometimes children look more like their mother than their dad, even though they contain the genetics of both. All right, we want to think of resonance structure sort of like that. All right, the real molecule looks like a combination of all of its resonance structures, but sometimes it will look more like one than the rest. Okay, so in this case, it's important to be able to identify the most significant resonance structure. All right, and there's rules for helping us identify the most significant resonance structure. And here are those rules, starting from A, which is the most important, the most significant, to the least important. All right, so whenever you draw out all the resonance structures for a molecule, you want to start off here with A and ask yourself, well, the most significant resonance form is going to have the greatest number of filled octets. All right, and then you're going to check that for all the resonance structures and see if one has the greatest number of filled octets in comparison to the others. If it does, that is the most significant resonance structure. If they all have filled octets, then you're going to move on to the next thing to help identify the most significant resonance structure. You're going to ask yourself, well, which structure has the fewest formal charges? The one with the fewest formal charges is going to be the more significant one. If all of them have the same number of formal charges, then you're going to move on to C, and you're going to ask yourself, well, the structure with a negative charge on the most electronegative element will be the most significant in comparison to the others. Well, if that doesn't help, if they all have a negative charge on the most electronegative element, then what we can say is that actually the resonance forms all have equivalent resonance structures. They're all equally contributing. So when A, B, and C cannot help you recognize a more significant resonance structure, then you can say that all of them contribute equally to the true resonance hybrid. All right, we're going to go ahead and we're going to do 1 to 2 practice problems to really understand this. All right, so for A, we're going to draw all the resonance structures for A. All right, we're going to draw all the resonance structures for A, and then after we have drawn all the resonance structures, then we're going to go through this list to see if there is a major resonance hybrid, all right? If there's a major resonance form, if one of the resonance structures we've drawn actually contributes more to the hybrid than the other structures, all right? So we're going to go ahead, we're going to draw A. All right, and we're going to try to draw the resonance structures for this molecule. All right, well, look at this. We have a negative charge near a double bond, okay? That means that there's a lone pair here, okay, near a double bond. What that means is we're going to take this negative charge, this lone pair, we're going to dump it right here to form a double bond right there. Okay, but if we form a double bond there, if we make a bond, we have to break a bond, right? So this double bond is going to break. It's going to dump its electrons right here at this position. All right, so we're going to go ahead. We're going to draw what that looks like. All right, now we have this double bond here. All right, and this negative charge right there, because we dumped the electrons. We dumped the electrons at that position. Well, do we see another resonance pattern? Yeah, look at that. Here's a double bond, and here's a negative charge in the allylic position. Perfect. That's a resonance pattern. And we know exactly how to do this, right? The lone pair, this negative charge, is going to dump its electrons here to form a double bond. All right, but if we make a bond, we have to break this double bond, and this double bond will dump its electrons right there. All right, so let's draw this resonance structure. That's going to look like this. All right, do we see any other resonance patterns? Yeah, look at this. This lone pair is now next to this double bond. All right, we know exactly how to do this. This lone pair is going to dump its electrons right there. We're going to form a double bond. But if we do that, then we need to break this bond. And that double bond will dump its electrons right there. So we're going to go ahead and draw that resonance structure. It's going to look like... It's going to look like this. All right. Now, again, we have a negative charge right next to a double bond. But hey, if we move this again, we're going to just come back to what we started off with. So we don't have to draw that because it's just going to be repetitive. All right. So now we have all the resonance forms for this molecule. Cool, we did that. Now we have to determine which structure is most important or most significant. All right, in order to do that, we're going to start off with our first rule, the most important. All right, does one resonance form have a complete octet where the others don't? Well, actually, if you look at all the molecules, at all the resonance forms, all of them are going to have complete octets. And you can double check this by counting the number of valence electrons, the number of electrons around each atom. They're all going to have satisfied octets. All right, and you can go ahead and count them. So all of them, all these resonance form, all atoms have complete octets. All right, so that rule is not going to help us find the more significant resonance structures. All right, so then we're going to move on to our next question, our next rule. All right, do any of them not have formal charges? Do any of these resonance forms not have formal charges? Well, all of them have formal charges. They have a negative charge. All right, the structure with the least amount of formal charges is going to be more significant, but every single one of these resonance forms actually has a negative charge. So they all have a negative charge. That's not going to help us determine which one is more significant. So we're going to move on to our third rule. Which structure has the negative charge on the more electronegative atom? Well, if we look at this first structure, all right, we're going to number them now. 1, 2, 3, 4. The first one has a negative charge on a nitrogen. All the others have a negative charge on a carbon. All right, so now when we ask which resonance form has the formal charge on the more electronegative atom, well, we can say that structure number 1 has a negative charge on the nitrogen, which is more electronegative than carbon, right? We can write that nitrogen is more electronegative than carbon. So structure 1 is the most significant. All right, so number 1, structure number 1, this one right here, is going to contribute the most to the resonance hybrid. All right, that makes all the other structures 2 through 4, the rest of them are all equivalent. All right, they're all the same because they all have a negative charge on the carbon. And so that makes the rest of those structures equivalent. All right, structure 1 contributes the most to the resonance hybrid. All right, and then structures 2, 3, and 4 all contribute equally second to the resonance hybrid. Fantastic. Let's do one more example. Let's do B. All right, we're going to do B. We're going to go ahead and draw first the resonance structure for this molecule. Do we see any patterns that we know? Yeah, look at that. Negative charge right next to a double bond. All right, we already know what to do. We're going to take that lone pair. We're going to dump it right here to form a double bond. But if we form a double bond, we have to break this one. And that double bond is going to dump its electrons at the oxygen. So now our molecule is going to look like this. All right. Well, again, we have a negative charge near a double bond, but hey, if we move this, again, we're just going to go backwards and end up at that first structure. So those are the only two resonance forms for this molecule. Now, if we go down our list, all right, they all have complete octets. Both of these structures and all the atoms in them all have complete octets. So that's not going to help us determine which is a more significant resonance form. So we move on to our second question. Fewer formal charges. Both of them have a negative formal charge. Both of them have this negative charge. Well, then we can move on to the third question. All right, the third question asks, well, which atoms contain the negative charges? In both cases, the negative charge is on an oxygen, so we can't compare, where is the formal charge, and choose the resonance form that has that formal charge on the more electronegative atom. That will be your more significant resonance form. The negative charge is on both of the oxygens, so that doesn't help us. The negative charge is on oxygen for both of these structures. All right, so that lets us conclude, last but not least, that these are actually equivalent resonance structures, resonance forms. They're going to both contribute to the resonance hybrid equally here. All right, and so that is how we want to approach these kinds of problems. I'm going to let C be one that you do, and I'll post the answers to that. Try it out. Draw all the resonance form for this molecule, all right, and then go through your rules to try to determine which resonance structure is more significant or if they're all equivalent. All right, let me know if you have any questions either by emailing me or leaving your questions in the comments below. And if you want more practice problems, then we can do more practice problems. Other than that, I hope this was helpful and have a great day.